In example 7, we're going to use a U-substitution and the log rule. And it says solve the differential equation dy dx equals 1 over x times the ln of x. Now they're asking us the question in a slightly different way. Here's how we can make it look more like what we're used to. The first thing we do is multiply both sides by dx. dy equals 1 over x ln of x dx. And if I take the antiderivative of dy, I get y. Y equals, and if I antiderive the left, I'll have to antiderive the right also, the antiderivative of 1 over x ln of x dx. So now it looks more like what the some of the other examples were asking us. Now let's see if we can fit this into the format. So we need to pick a u. U equals what? Is it going to equal the whole denominator, just the x, or the ln of x? Well, remember we want a function and its derivative. What's the derivative of x? Just 1. What is the derivative of ln of x? Well, that's 1 over x, and that's what we have right here. So it looks like our u substitution is going to be u equals the ln of x. And then the derivative with respect to x would be 1 over x dx. So it looks like we have everything we need. And we could even rewrite this to make it look a little more like what we need. So we have y equals this 1 over x, or just if we concentrate on the x in the denominator, I can pull it out and make it part of its own fraction. 1 over x times 1 over the ln of x dx. So I broke it into two pieces. 1 times 1 is 1, and x times ln of x is my denominator. And if this whole thing here was just a number like a 3, I could just move it up top. 3 over the ln of x. Well, we can do that even right now. We can have our antiderivative. I can move this piece up to the numerator. 1 over x, and then I'll have my big divider line, and then my denominator is the ln of x, and I'll have my dx. So it might be easier to see this way that it does fit the format that we're looking for. Our denominator is a function, the natural log of x. Our numerator is that function's derivative. Here's the ln of x. That function's derivative is 1 over x, and that's exactly what we have up top. So we are ready to take the antiderivative. And when we do so, it's going to be the ln of the denominator. And that denominator is, or our u value, the ln of x. So look at that. The natural log of the absolute value of the natural log of x. And then we add our plus c, our arbitrary constant. So it took a little bit of maneuvering around, or the more you do of these, the more you train your brain and your eye to look at them and start picking things like that apart. Now on to integrals of the trig functions. In a previous section, we looked at the 6 trig integration rules, the 6 that correspond directly to the differentiation rules. With the log rule, we can now complete the set of the basic trig integration formulas. If we think back, we want now the antiderivative of tan of x. Well, what do you derive to get tangent? Well, if we derive tangent, we get tangent times secant. If we derive secant, we get secant or tan squared. So we don't have anything right now that fits this format. But if we think back to pre-calculus, what's another way to write tangent? Well, that'd be 1 over cotan or sine over cosine. So I can rewrite tan as sine over cos. If I look at my denominator, that is a good choice to maybe make that my u. So u equals cos of x, and the derivative of that, du, the derivative of cosine is negative sine x, and we multiply both sides by dx. So we have almost exactly what we need. We just need to tweak it with a negative here for the sine of x, and we'll have to tweak that with a negative out in front of the integral. So we are now in the format. Our denominator is a function, the numerator is its derivative, this sine x dx negative is going to be our du, so we have u prime over u. And we can apply our integration. We're going to have negative the natural log of the absolute value of our denominator plus c. Example 8 uses a trig identity to derive an integration rule for the tangent function. This next example takes a rather unusual step, multiplying and dividing by the same quantity to derive an integration rule for the secant function. Hats off to whoever came up with this technique. So we have our antiderivative of the secant of x dx. What did we derive to get secant? Well, there was nothing straightforward that we derived to get secant. So somebody a long time ago sat back and was puzzling over this and wanted to get this to fit the format for integration with the natural log function. And somehow they came up with this. This is secant of x over 1, and I'm going to multiply the numerator and the denominator by the same quantity. And the quantity that they eventually settled on was secant x plus tan x. Secant x plus tan x. And if I multiply the numerator by that, it's only fair that I multiply the denominator by the same quantity. So if I do my distribution, I'll still have my antiderivative sign. When we distribute here, we're going to get secant times secant is secant squared of x. Plus, here we will have secant times tan, and we'll just leave that as secant x tan x. And that is all over. It's just secant plus tan times 1, so it just stays secant x plus tan x. Now, let's see if that helped at all. I look at my denominator. My denominator is two functions added together. What is the derivative of secant? Well, remember I had that little trick. You do the SST, and that is secant tan. And if we derive secant, the derivative of secant is secant times tan. So the derivative of this term, secant, is secant times tan. And the derivative of tan, we go this way. Secant times secant, or secant squared. So look at that. It does fit the format. And let's, write this out and make it all official. We're going to let u equal secant x plus tan x. And du is going to equal our numerator, secant squared x plus secant x tan x dx. I'd have to squeeze that in. Oh yeah, we need a dx in there. So a lot of stuff going on here, but now it does fit our format. We have a denominator is our u. The numerator is its derivative, u prime, or du. So we can do the integration, and that's just simply going to be the natural log of the absolute value of the denominator plus c. And might as well plug our u value back in. Our u value is secant x plus tan x plus c. Again, hats off to whoever come up with that. With the results of the last two examples, you now have integration formulas for sine x, cos x, tan x, secant x. All 6 of the trig rules are summarized below. For proofs of the cotan and cosecant function, those are exercises 91 and 92 in your book. If those aren't assigned for homework, we will do those in class. So, here are the ones we've known these before. The antiderivative of sine is negative cos, and the antiderivative of cos is sine, because we know the derivative of sine is cosine, and the derivative of negative cos is positive sine. We just derived the tangent one and the secant one. Example 10, and this here is a definite integration. We have lower and upper limits. And this we can, if we remember our pre-calc, we can simplify this quite nicely. So, underneath the radical, we have 1 plus tan squared. If we think back to pre-calc, we had a trig identity. Remember the Pythagorean identity, sine squared plus cosine squared equals 1. And there was another one, 1 plus, and I'm going to abbreviate, tan squared equals secant squared. So this 1 plus tan squared under the radical, we can replace with a secant squared. So the square root of secant squared of x dx. And look just how perfect is that. We have a square root with a squared underneath it. So those will cancel out. And we'll have our definite integral from 0 to 1/4 pi of just secant of x dx. And with the new formulas that we just figured out and saw in that previous slide, the antiderivative of secant x is the ln, the natural log of the absolute value of secant x plus tan x. And there would be no plus c. This is a definite integral, and that is from 0 to 1/4 pi. So let's evaluate. Plug in our upper limit. 1/4 pi goes in for both x's. So our first term is going to be the ln of the absolute value of secant 1/4 pi plus tan 1/4 pi. And then we will subtract when we run our lower limit through. The natural log of the secant of 0 plus the tangent of 0. Now, how well do we remember our unit circle? So the ln. Secant of 1/4 pi. 1/4 pi is in the first quadrant. Our cosine value is √2/2. Our sine value is √2/2. Secant is the reciprocal of cosine. So if we flip this over, we have secant. And if we flip that over, it's going to be 2 over the square root of 2. And if we rationalize our denominator, we're going to get 2 square roots of 2/2, and those 2's will cancel. So that value is simply the square root of 2. Plus the tan at 1/4 pi. Tan is sine divided by cosine. Anything divided by itself is 1, so we get the square root of 2 plus 1 in our first set of absolute value bars. Minus the ln of secant of 0. Now we're down here at a 0 angle. This point is 1, 0. Again, secant is the reciprocal of cosine. The reciprocal of 1 is 1. Plus the tangent of 0. Tangent, again, is sine divided by cosine. 0 divided by 1 is 0. So we have the ln. And I guess we can drop the absolute value bars now because we know these are both known positive quantities. Root of 2 plus 1 minus, and here we will have the ln of 1. And from the previous example, I hope you remember that the ln of 1 is 0. So our final answer is the natural log of that quantity, √2 plus 1. And if we punch that into the calculator, we will get approximately 0.881. Example 11, last example. Average value of a function. Remember, average value. Average value. The only thing difference is we put in front of our antiderivative sign, our integral sign, 1 over b minus a. B is our upper limit of integration, a is our lower limit of integration, and then we just do our antiderivative or indefinite integral, definite integral of whatever function we're dealing with. Here it is the tan of x. So let's set this up. 1 over b minus a, and that's going to be pi over 4 minus 0. Pi over 4 minus 0 is pi over 4. And we'll have the definite integral from 0 to 1/4 pi of our tangent function, tan of x. And 1 divided by this fraction, we bring that fraction up and flip it. So that is going to be 4 over pi. The antiderivative of tangent, the formula we just learned, is the negative natural log of the absolute value of cos of x. And we'll close that off, and our limits are from 0 to 1/4 pi. So let's run our limits through that function and see what pops out. So we're going to have 4 over pi. Plug in our upper limit. Negative the ln cosine of 1/4 pi. Back to here, cosine value, this again was a 1/4 pi angle. Cosine is √2/2. And we can drop the absolute value bars, I guess, because we know that is positive. So we're looking at the natural log of √2/2. And then minus the negative natural log. We plug in 0. Cosine of 0, cosine again is our x coordinates, that would be a 1. Negative natural log of 1. And then we close off our parentheses. So, we have 4/pi. We can drag this negative sign out front. Negative 4/pi. Natural log of √2/2. And these negatives would cancel. Minusing a negative is adding the opposite. But it doesn't matter in this case because we know the ln of 1 is equal to 0. So we're just left with negative 4/pi times the natural log of √2/2. It's better to leave it in that format. That is more precise. But if they do ask for a decimal, estimate or rounding off, it's approximately 0.441, I believe. Yes, 0.441. And remember, that's our average value. That is where we would hit on the y-axis. Here would be 0.441. If we made this into a rectangle, that's a terrible line there. So if we were to just look at this rectangle I'm highlighting here with the black marker, the area of this black rectangle is exactly the same area as the area under the curve, or its average value.